Hello everyone, hope everyone is doing well. In this lecture, we will learn how to evaluate our null and alternate hypothesis at different critical values. When we were talking about two-tailed test, and this is an extension of that video we talked about two-tailed tests, and that I will provide a link below. We talked about finding the 95% confidence interval, or alpha is 5% critical value, where we were talking about if you have a number, let's say if any number mu equals, let's say 40, then if we were to test if some sample, let's say I have a sample where the x bar equals 33, then is this sample actually from a population with this mean, or is it that the population mean has changed? So we talked about in that previous lecture that we create thresholds, and we say that because of, let's say, as we learned in central limit theorem, is that if this is my mean, then 95% of the values or of the means of the samples will be within this range, and 5% will be outside of this range. And so 5% can't be in one area, so if 95% is in this range, 2.5% is to the left and 2.5% is to the right. And then we say that if this x equals 33, if it falls in this range, we say we reject the null. But if it falls, let's say, in this range, then we say we do not reject the null. Now this range, in that previous video, we talked about where the critical value, alpha, was at 5% critical value. So, however, there are different levels of alpha that we can choose from, and that depends upon the researcher which one they want to choose, and also maybe in your stats questions you may have different levels of critical values that you use to evaluate the null and alternate hypothesis. So the critical values that we generally use are where alpha is either at 10%, or at 5%, or at 1%. So alpha can be any of these three values. So we will look at three different, we will look at the same question and we will see how do we evaluate it at different levels of alpha. And then we are going to see what kind of statement we write based on the critical values we have. So let's look at one example. Let's say that we have the average time for a 100-meter dash is 13.4 seconds. Now this has been, we can say that this value that we have, this is our mu. But in the current meet, there were 50 participants, so this is my sample. And the mean time was 11.5 seconds, and the standard deviation is 1.8 seconds. So notice that the population sigma is missing here. So we basically write it down here. So since the population standard deviation is not known, we are going to use the t distribution in this case. But before we do that, first we have to first frame the hypothesis question and the statements, and then we will evaluate it at whatever critical value the question says. Now the question is asking at 5% critical value. So the first step is coming up with the null and alternate hypothesis. Now we have to test are we doing a one-tail test or two-tail test? In our case, it is saying that test at the 5% level whether the average time is different, which means that it could be greater than mu, it could be less than mu, or it could be equal to mu. We just don't know which one. So as a result of that, this is my hypothesis test. So basically, the null is the population mean has not changed. It is still at 13.4 seconds, and the alternate is it is no longer 13.4 seconds. I can also write it this way in a shortened form. Either one is correct. Again, a reminder, if this is my hypothesis statement, this is what we are testing. And if you notice here, we are using mu's. So we are evaluating, even though we got our data from a small sample of 50 participants, we are evaluating mu. So if I actually wrote x naught, x bar equals to 13.4, and alternate is x bar is not equal to 13.4, this statement would be wrong. So we should not evaluate the hypothesis statement for x bar, for the sample mean. We should always do it for the population mean. So then we have our data. We collected the data. That's my step 2. I have n is 50. My x bar is 11.5. S bar is 1.8 seconds. And then finally, in the previous lecture, we talked about that this is where we analyze the data. So instead of saying analyze the data, we are now going to say calculate the t-stat. So the t-stat, this is the formula, x bar minus mu divided by the s bar divided by the square root of n. Now, s bar over the square root of n, this is called the standard error. So this has a special name, and we use that in the denominator. So instead of writing it that way, I could have also written a standard error. So the numerator we have is x bar minus mu, which is 11.5 minus 3.4. The denominator is, since my standard deviation, sample standard deviation is 1.8 seconds, which I've also written here. It is 1.8 divided by the square root of 50. So I get these two numbers. So then my t-stat is basically, this number is basically going to be negative 1.9 divided by 0.254. And I get the value as 7.46. Then this fourth step that we should do is find the critical values. Now in our case, since it's a two-tailed test, because the alternate is saying that the population mean could be less than 13.4 or greater than 13.4. So if I were to draw the critical values, then if my mean were actually, let's say hypothetically, this is what I'm testing, then these are the two levels I should find. But I don't know this value yet, so what I can do is convert this value into the t-distribution. So basically I center it around 0, and then my t-value would be, the lower one would be, and my degrees of freedom is n minus 1. So I get this value. And so the other side would be the opposite value. So this is now my critical value, which is 2.009. Next I will find, is this value, what I should do is, since you can see, since it's a symmetric distribution, the top and bottom ones are the same. So I can draw my distribution and I can see where does my t-stat lie. So I can see that. So if I draw my distribution, I can see that if this is centered around 0 and the lower critical value is -2 and upper one is +2, the t-stat that I calculated is somewhere way around here. So it was like -7 point something. So it is outside of these critical values. So what we would say then in our statement here is the t-stat, or just to make it easier, because sometimes it's less than that, sometimes it's greater than that, what we will do is just drop the negative sign, and we will say the absolute value. So what this means is I'm saying that this value, the absolute value that I have, I'm dropping the negative sign, so it becomes 7.46. 7.46, this value is definitely greater in magnitude than the critical value of t. And just to make it a little clearer than that, So the absolute value of the t-stat is greater in magnitude than the absolute value of the critical value of t, which is just saying that we're removing the negative sign. So even if the t-value was way out here, negative 7.46, we are saying once we remove the negative signs, the order gets flipped. So now 7.46 is definitely greater in magnitude. So we can reject the null hypothesis. So after we find the critical values, this is what we can write. And we can say that, consequently, because the critical value of t is 7.4, or because the critical value of t is less than 7.46, so we can reject the null. Now, and this is one way of finding whether the null hypothesis is rejected or not. Another way of doing it is what we would call by p-values. P-values are basically the same thing as t-values. If you think about like how we measure distances, we can measure distances by kilometers or by miles or by feet or by yards. We can find or we can evaluate null hypothesis by using t-values or t-distribution or by p-values. What p-values does is that since I have this t-stat distribution, my p-value is going to be t.dist. My x is minus 7.4639. Degrees of freedom is 50 minus 1. And cumulative, I'll say, is true. And then I'll also say times 2. And I get this number is a very, very small number. Now, what does this number mean? What p-value is telling us is that, let's say if I draw this diagram again, or let's say this is the t-distribution we have, and this is the t-value, -2 and +2. And I found that my t-value is way out here, which is at -7.46. What this p-value is saying is that this is the probability that I am either to the left of this value and the reason we multiply it because it's a two-tailed test, so it could also be on this side. So it is also the probability to the right of 7.46. So this p-value is basically finding the probability to the left of 7.46, and since it is symmetric, it is also, we multiplied by 2 to find the probability to the right of 7.46. So that's another way of finding it. Now this number, as we can see, is very small, and since our critical value is, we are evaluating it at alpha equals to 0.05 according to the question. So this is basically saying if, let's say, the p-value that we calculated is greater than 0.05, we do not reject the null. If p-value is less than 0.05, we reject the null. Now, what if p-value is equal to 0.05? Then it's your call. Some books say you should not reject it. Some books say you reject it. But usually the p-value is rarely at exactly 0.05. So we can see here that the p-value is very low. So we will say that the p-value is less than alpha, which is 0.05 in our case, and that's the question asked for. So we reject the null. So we could use either t-values or p-values to evaluate our hypothesis. But basically, they're both giving us the same answers. Now let's look at another example. Here we looked at the 5% critical value. what if we were to find the 10% at 10% critical value? So everything remains the same. Steps 1, 2, and 3, instead of saying analyze data, we will say calculate the t-stat. So all those steps are the same, and we find our t-stat. But now my critical value is a different number. So in step 4, I will say find the. So the critical value of t here would be, so it will be plus minus 1.67. So in our case, we see that our t-stat is a much higher number. We find that our t-stat is negative 7.46. So if I drop the negative sign and just take the absolute value, it becomes 7.46339. So again, I will compare it with my critical value of t, and I'll find that, okay, well, the interpretation is the same, the absolute value. So we can now write that the absolute value of the t-stat is greater than the absolute value of the critical value of t when alpha is at 0.05. And so we reject the null. Now, if I did the same thing with my p-values, so right after finding the t-stat, I would find the p-value, and that would be equal to t.dist, and I would use this value as my x. My degrees of freedom is 50 minus 1, and cumulative I would say is true. Since it's a two-tailed distribution, I will multiply it by 2. And I get a very small number. It's actually very close to 0. So now I will say that the p-value, so we will now say that the p-value is less than alpha, which is 0.1, so we reject the null. And then the next example is basically the same question, but now let's say I want to test it at 1%. So everything else remains the same. Instead of analyzing the data, I will calculate the t-stat. And then finally, in step 4, I will say, so in my case, everything else is the same, but I'm now testing it at 1% critical value. So at 1%, it will be 2.67. And we find the same interpretation here is that. So here we would say that the absolute value of the t-stat is greater than the absolute value of the critical value of t, which is 2.67. And of course, my t-stat was 7.46. So we reject the null. Now, if I were to find the p-value, so the p-value here would be, and so this is my p-value. And now I would say, well, the p-value, so here I see that the p-value is less than the value of alpha. So we reject the null. So in either case, as you can see, up to find step 3 is the same. So if I use t-values or p-values, in step 4, I can find the critical value of t, and then I can evaluate the critical value of t, or basically compare the critical value of t with the t-stat right here. Or instead of doing that, in step 4, I could convert the t-stat that I calculated into a p-value, and then use that p-value and compare it with alpha to see that if it's less than alpha, we reject the null. If it's greater than alpha, we do not reject the null. Now, yes, there would be cases where basically you would see that you may reject something at 5%, but not at 1%. So that's where it comes to the researchers' basically preferences to choose which level of alpha to choose. Now, this was for a case where we have no information about the population standard deviation. What if we do have the information about the population standard deviation? So in that case, we are given mu, which is that, and we also have sigma given. So in that case, the null and alternate remains the same. The question is exactly the same. We collected the data. Now, in my case, instead of analyzing the data, we are now going to find the z-values, or the z-statistic. So the z-stat, this is the formula, which is x bar minus mu. If you notice, it's very similar to the t-stat, except for instead of using s bar, which was this number, I am now using sigma, which is the population standard deviation. So that's one thing we replaced, and then we found out here's the numerator, which I get to be negative 1.9. The denominator is 2.5 divided by the square root of 50, which is n here. And then I find that instead of t-stat, this will be my z-stat. It will be negative 5.37. After that, step 4 would be find the critical values of z. So again, just like because it's a two-tailed test, we can find the two sides of it. And we are testing it at 5%, as we said. So my z value would be, it would be norm.s.inv 0.05 divided by 2. And I get this number. So again, I will compare my z-stat with the critical value of z. And I can see if I drop the negative value, I will say, so the absolute value of z that I calculated, which is negative 5.37, that is larger than, in magnitude, than the critical value of z with the absolute value of the critical value of z. So therefore, we reject the null. So the process is the same. We're just using a different test statistic and a different critical value. Now, just like with t-values, we could have used p-values to evaluate. So instead, what we could have done is find the p-value, which would be, so the number would be norm.s.dist. That's the z-value, comma, true times 2. And we find this is a very small number. And to evaluate it, we would say that, since we are evaluating at 5%, so we would say that the p-value is less than the alpha, which is 0.05. So we reject the null. So here we're comparing this p-value with alpha, which was given here. Since it's saying test at 5%, so that is my alpha. Now let's say I want to test it at 10%. So again, everything else remains the same. This is my z-stat. And so here's my null and alternate hypothesis. These are all my data. I plug in the z-stat equation to find my z-stat value. Now, in step 4, I would find the critical value of z. Now, since it's at 10%, the formula will be norm.s.inv 0.1 divided by 2. So I get this value. And this is the z-stat I have. So again, I see that if I take the absolute value, if I drop the negative sign, 5.37 is greater than the absolute value of this number, which is 1.64. So I would say that, so the absolute value of the z-stat is greater in magnitude than the absolute value of the critical value of z, so we reject the null. This is one way of doing it. And then just like that, if I were to find the p-value, I would have done norm.s.dist. So this would be my z-value, or the probability. And then I would just say, since my alpha here is at 0.1, so I would say that the p-value, so the p-value is less than alpha, which is 0.1, so we reject the null. The question may also come as asking you to test it at 1%. So again, everything else remains the same, just at the time of, us coming up with the critical value. So in step 4, we would say, and so in this case, we are going to say, so my critical value at 1% for two-tailed test is going to be negative 2.57 and 2.57. So we drop the negative value just so that it's easier to interpret with or compare it with my z-stat. So again, we would say that the absolute value of the z-stat, which turns to be 5.374, is greater in value or in magnitude than the absolute value of the critical value of z, which the absolute value becomes 2.57. So if that were the case, then we reject the null. So again, we can also do the same calculation by using p-values. So we would say, so this is my p-value. Now I will compare the p-value to the value of alpha, which is, for this question, is at 1%. So we would say the p-value is less than alpha. So we reject the null. So here in this example, we use the same question, but tested it at different levels of critical values and whether we know this population standard deviation or not. So I know we did the same thing 6 times, but it's just showing you that when we have different critical values and different information given, how even though our z-stat hasn't changed, our t-stat hasn't changed, our critical values that we are using to compare the z-stat or t-stat with are different, so we may get different numbers. So for example, supposing my z-stat came out to be, let's say, 2.34. Then in that case, if you notice that the z critical at 95% or at alpha equal 0.05, that is 1.96, but z critical at alpha equals 0.01 is 2.57. If the z-stat is 2.34, you would see that I would reject it at 5% alpha. So we would reject, if I'm using this value, I would definitely reject. But at 2.57, I would see that, well, the z-stat is actually less than the z critical. So if I were using that critical value, I would not reject the null. So therefore, the critical values are important. Now, which one is correct? Well, that's a little bit of a gray area. There's really no correct answer here. It's basically what we're using to evaluate that answer. And it's usually good to stick to one. Like in economics, we just stick at alpha is at 5%, and we use that for almost all our analysis. So hopefully this was helpful, and I will see you at a later video. Have a good day.